Hello everyone. In this video we are going to discuss about modeling and FFT analysis on PCC. That is a point of common coupling. It is an inverter-based microgrid droop control technique example using Matlab Simulink. This example shows the islanded operation of an inverter-based microgrid using droop control technique. Here these are the contents inverter-based microgrid design using droop control technique. The contents are introduction about islanded microgrid operation and what is droop control method and the Simulink model of inverter based microgrid design and what is point of common coupling measurements, what are the requirements, and Matlab powerFFT app. This powerFFT app used for fast Fourier transform analysis on the PCC. Total harmonic distortion and harmonic analysis can be done by using this interactive powerFFT app. Finally, we are going to see the simulation and result analysis. What are the products you need to design this inverter based microgrid with droop control technique? That is a Matlab and Simscape electrical toolbox. Here a small introduction about islanded microgrid operation. What is a microgrid? First you will see what is a microgrid. A microgrid is said to be in islanded mode when it is in disconnected from the main grid and it operates independently with micro sources and load. These are the common definition of islanded mode. Islanded mode refers to the case when a circuit breaker isolates the microgrid from the rest of the utility grid. Another one, what is the main objective of this microgrid in islanded mode is to allow the system to operate even in adverse scenarios such as fault in main grid, high prices of main grid powers, and supplying remote areas. Here what are the three important controls in microgrid operation? First one is a primary control. In this primary control, room method is used to evaluate the behavior of synchronous machines. In this level, the virtual impedance can also be implemented to improve the X/AR ratio. The next method is secondary control. Here guarantees the restoration of frequency and voltage by changing the operation set points of the primary control. This level also can include a strategy to resynchronize the microgrid with the utility grid. The final one is the tertiary control. This controls the power flow between microgrid and utility grid and also executed only when microgrid operated in connected mode. Then what is droop control method? Droop control is a well established technique to control an autonomous grid. Here what is droop control method? Droop control is a key solution for sharing the demand power between generators in autonomous microgrids where there is no support from the electricity distribution grid. So it is a very well technique to control an autonomous grid. It is also commonly used as speed control mode of a governor of a prime mover driving a synchronous generator connected to a load. This figure shows the droop characteristic of the inverter control, and this droop, this where power versus frequency is set to 1%. This one 1%, meaning that microgrid frequency is allowed to vary 60.3 Hz. That is the inverter producer no active power to 60.3 Hz to 59.7 Hz. That is the inverter produces its normal active power. The droop Q/V is set to 4%. The next diagram shows this droop Q/V is set to 4%, meaning that the microgrid voltage at the PCC bus, that is a point of common coupling PCC bus, is allowed to vary from 612 VRMS. That is a inverter produces full inductive power to 588 VRMS. That is a capacity power. Note that here this Q max is specified as the half of the nominal active power. It is P norm. These are parallel connected inverters in microgrid configurations. Here it is a droop control applied in each and every inverter. Is a voltage controller and a PWM generator feeding the inverter also there. Finally, a dynamic load model here used for this one. This figure shows the droop characteristic of the inverter control. What all the blocks are needed? Droop control block and voltage controller and PWM and inverter and finally load. Each and every inverters having the subsystems. In this example, the microgrids consist of three parallel inverters. This one, 3 parallel inverters subsystem with power ratings of 500 kilowatts, 300 kilowatts, and 200 kilowatts respectively. Here the dynamic load model is used to dynamically change the microgrid total load. Here each subsystem also includes a control system and a SPWM generator feeding the inverter. Okay, this is a general model of this example. And this simulating diagram shows modeling and analysis of inverter-based microgrid with Droop Control Technique. Here these are the subsystems are there. First to control subsystem, the 3 inverters connected in parallelly, and finally this is a common PCC bus connected to the point of common coupling bus. These are the 3 different loads and PCC measurements. Here by using this example, can measure the PCC frequency and power and active power and reactive power, frequency versus voltage also we can find out. Here what is a Droop control? Droop control method is a well established technique to control an autonomous grid. Here in this control system toolbox, load is increased at 1 second and Droop control enable at 3 seconds when we are going for simulation. The first one load increased at 1 second and Droop control enabled at 3 seconds, and finally the supervisory control enabled at 5 seconds. What is the supervisory control system? This is a microgrid supervisory control system. When enabled, modifies the inverter active power versus frequency and reactive power versus voltage. There is a Q by V. Droop set point in order to bring back the microgrid frequency and voltage at the nominal values. Here normally the 60 Hz and 600 volts respectively given. In this example, it illustrates the operation of an inverter-based microgrid disconnected from the main grid. That is a islanded mode using the Droop control technique. With the Droop control technique, PLL are not required to achieve system-wide synchronization because all the inverters reach the same frequency. We are set the same frequency as 60 Hz only. Let us see what are the setting parameters are there. In next slide we are going to see. The microgrid consists of these 3 parallel inverter subsystem with power ratings of 500 kW, 300 kW and 200 kW respectively. It is all the 3 inverters, parallelly connected inverters connected with the common PCC, point of common coupling bus. Okay, these are the different types of load. Here what are the measurements? Here P refers active power, F refers frequency, and Q refers reactive power, and V refers voltage. Okay, then the inverter subsystems. What are the 3 different inverter subsystems connected with PCC bus? Okay, here when you double click on this microgrid supervisory control block, this control block, we are getting this window. Here itself you can set the parameters for this is for inverter 1. 60 Hz frequency and line voltage we given as 600 VRMS, and what is the frequency controller and voltage controllers are there. Here itself you can set the PI gain, that is a proportional gain and integral gain. You can set the upper lower limits, output limits in terms of hertz. Here V frequency regulator proportional gain set to 0.03 and integral gain is 2. Here the voltage regulator proportional gain 0.1 and integral gain is 7. Measurement filter rates in terms of 10, sample time 3 seconds. Here this microgrid consists of 3 parallel inverter subsystems with this 500, 300 and 200 kW bus. A dynamic load is modeled to dynamically change the microgrid total load. Here this is microgrid supervisory control. We set this 60 Hz and 600 line voltage, 600 voltage. Each inverter subsystem contains a 3-phase 2-level power converter, an LC filter, a 480 cross 600 volt transformer, as well as ideal DC source to represent the DC link of typical renewable energy system generation such as PV array, wind turbine and battery energy storage system. Each subsystem also includes a control system and a PWM generator feeding the inverter here. Here what are the 3 parallel inverter subsystem block parameters setup? Here these are first one, first inverter, that is a 500 kW, and second one inverter 2 300 kW, and third one inverter 3 200 kW. Here itself we can set the parameters of these nominal values. What about the power is 500 VA and the frequency is 60 Hz, and primary line voltage is 600 and secondary line voltage is 480, DC link voltage is 1000. Here you can set the droop values. What is a droop? Frequency percentage 1, voltage droop droop is 4%. Previously we discussed in this slide. So the droop value set for 3 inverters, frequency droop is 1%, and voltage droop is 4%, and the proportional gain it is vary with inverters. The first inverter proportional gain is set to 2 and integral gain 4, here 2, 10, here 2, 12. So in the same manner, you set the current regulator values is same to all the three inverters, that is a 0.3 and 20. And what is the PWM frequency, PWM generator? Here itself you have to give the switching frequency and carrier initial phase in terms of hertz and degrees. Here 2700, here in this 200 kilowatt system as 2340, and the carrier initial phase are set to first inverter and second inverter 90 degree, and final one, that's the third 200 kilowatts inverter, you set the carrier phase initial phase as 0. Here the measurement filter F1 value is 500 Hz for all the three parallel inverters. This analysis is based on the frequency reference that capable in generating the output of voltage and current as well as the equality of load power sharing when a load disturbance occurs in the parallel connected inverters. Okay, and then the next one, another one, these are load. This output side, three different loads are modeled, used to dynamically change the microgrid total load. First common point of common bus, coupling bus, load 1, load 2 and variable load. Here this diagram shows block parameters load, that is a load 1. Here the configuration is Y grounded configuration. Here you have to apply the nominal phase to phase voltage, that is Vn is 600 volt and nominal frequency is 60 Hz. This is for first load. Also you have to specify the PQ powers, that is active power is a 400 and inductive reactive power is 100 and capacitive reactive power is, you set the negative variable value is 0. Similarly you set the load 2, double click on this block, you are getting this type of window. Here itself, and you have to set the nominal phase to phase voltage and nominal frequency and the active power. Previous one for load 1 we have set this 400 and here active power is 50. In this manner you have to give. The final one, there is a variable load. This variable load implements 3-phase, this one 3-phase 3-wire dynamic load. This is active power P and the reactive power Q absorbed by the load vary as a function of positive sequence voltage. So that you have to give the parameters values, nominal LL voltage and frequency and active reactive power at initial voltage and initial positive sequence voltage also you have to mention here. This is the final one. This is the PCC measurement blocks. In this measurement block shows the PCC frequency in terms of hertz, frequency power and reactive power and active power and voltage, and finally you can see the PCC measurement at the time of simulation. Okay, then what is point of common coupling measurement subsystem having? This point of subsystem measurement, this PCC measurement block, you need to measure this PCC voltage controller subsystem. Here under this PCC voltage measurement subsystem we are getting this type of PLL, that is a power, PLL driven power and fundamental PLL driven power also. You need to understand this concept. What is the point of common coupling? This is the point in the electric circuit where a microgrid is connected to a main grid. Here there are the three different types of PCC voltage controllers are there. PCC voltage controller with a proportional gain and PCC voltage controller with a proportional gain and a first order lag element, and the third method is PCC voltage controller with a proportional gain and integrator. Here we are using proportional gain and integrator. Here we are using voltage regulator and current regulator for these three subsystems, three inverter subsystems. Here these are microgrids that do not have a PCC are called isolated microgrids, which are usually present in remote sites, for example remote communities or remote industrial sites, where an interconnection with the main grid is not feasible due to either technical or economic constraints. In addition, the power sharing also among each inverter can be achieved, since each inverter gives the power in proportionate to its capacity. Okay, here in this type of design with the Droop Control Technique, PLL are not required to achieve system-wide synchronization because all inverters reach the same frequency. Okay, here Droop characteristic of inverter control. Here what are the blocks are there in this Droop control method subsystem. Here measurements based on the frequency value given by Droop control, the measurement subsystem computes the active and reactive power generated by the inverter. It also computes DQ components of three-phase voltages and current in the microgrid PCC bus. Here what is a voltage regulator block, what is a current regulator block, what is a V reference generation. Here voltage regulator is reference voltage V reference given by the Droop control is fed to the voltage regulators. This type of regulators process the measured DQ voltage and reference voltage VRF to generate the reference current ID reference and IQ reference, reactive and active currents. Then next one, the current regulators, the ID reference and IQ reference currents are fed to the current regulators. This type of current regulator process the measured and reference current to produce the required DQ voltage for the inverter. Then next one is the VDVQ conversion, that is a V reference generation are scaled and transformed to a three-phase signal V reference feeding the PW modulator generating pulses to the inverter. At the time of simulation, we are going to see what is ID reference, what is IQ reference, what is the VDVQ voltage VRF generation also we can see. Then the next one is the interactive Matlab FFT Analyzer app. It is introduced in 2020, I think version only supports. It is an interesting one to analyze the power FFT app. Here in this type of FFT analyzer, to perform Fourier analysis of simulation data signals. Whatever the at the time of simulation, you need to set the power values in terms of workspace. In this workspace, we are the structure with the time variables parameters we need to set. Okay, in this window, what are the structures are there? If FFT analysis block, this is a selected signal with this FFT window, and next one is you can see the magnitude of is fundamental frequency, or THD refers to the total harmonic distortion in terms of frequency versus magnitude. The FFT analyzer app, what is the use of this interactive Matlab FFT analyzer app? This app allows we to perform Fourier analysis of simulation data and provides access to all the simulation data that are defined as a structure with time variables in our workspace, Matlab workspace. And the app displays the spectrum. Here the spectrum as a bar graph or a list of percentages related to a base value or DC component of the signal. How to get this app? Okay, in this Matlab command prompt, just you need to type power FFT. You will get this type of window. Through this our workspace at the time of simulation workspace, this variables structure with time variables also generated. By using this value, the power FFT app automatically displays the spectrum as a bar graph or list in percentage related to a base value or the DC component of the signal. Here click this compute FFT value, you are getting this bar graph or spectrum. Okay, then after simulation we will get this inverter scope. What are the three inverter scope? So first one 300, 500, 300 and 200 power we are going to see here, P and Q value, reactive power and active power. These are power scopes, the inverter scopes it shows here. By using this interactive tools, we can measure the bi-level measurements. It shows amplitude and edges, what is the rise time, what is the slew rate, and overshoots, undershoots, cycles, and cursor measurements also possible, and signal statistics and peak finder also possible. Here you can see that at the 1 second the total microgrid load is increased from 450 kilowatts or 100 kVA to 850 kilowatts to 200 kVA. At 3 seconds Droop control is enabled on all the inverters. We can see the microgrid load is now shared equally among the three inverters. At 5 seconds the supervisory control is enabled. The frequency is then being slowly increased to 60 Hz and the voltage is 600 volt. Okay, the next one is the PCC scope. Previous one is a inverter scope. This is a PCC scope. It also the droop on the power and frequency is set to 1%, meaning that microgrid frequency is allowed to vary from 60.3 Hz, that is a inverter producer no active power, to 59.7 Hz. This is a P refers active power, Q refers reactive power. Okay, here in this window PCC frequency is a reactive power and reactive power of at PCC bus, and the next one is a PCC VAB value. This droop Q by V is set to 4%. That's a droop value set is 4%, meaning that the microgrid voltage at PCC bus is allowed to vary from 612 VRMS to 588 VRMS. Note that here Q max is specified as the off of the nominal active power, P norm. Here you can see this one 59.7, that is a 60.3 to 59.7 hertz. Here this value, that is where 612 VRMS to 588 VRMS values. Okay. Then after simulation we are getting this type of power FFT analysis. Here what is this FFT window shows what is the frequency versus magnitude. This is a power scope bar graph shows. To demonstrate the impact of the inverters, PWM carriers initial phase on the PCC bus voltage harmonic content, first to open the FFT analyzer app to perform an FFT analysis of the PCC phase A bus voltage. In this app, set the structure with time parameters. Carefully note down these values to get this analysis of PCC voltage. So you can see this one in this app. Set the structure with parameter to PCC. The signal parameter is you set VPCC. You need to select this VPCC and the dimension parameters to 1. Dimension you set 1, and the analyze the PCC bus voltage. Set the zoom on parameter to FFT window. Here you need to set this zoom on. You have to select these parameters, zoom on parameter to FFT window. The start time you set 7.9, and maximum frequency parameter is 7000. You need to set 7000 here, 7000. Click compute FFT. In the FFT plot, the maximum harmonic occurs around the switching frequency of 2700 Hz and is close to 2%. Okay, next one, now double click on the inverter 2. Now the parallel double click on inverter 2, that is a 300 kW subsystem, and change the carrier initial phase parameter to -90 degree. Rerun the simulation and again perform an FFT analysis on PCC phase A voltage. Now we need to see that this new carrier phase setting significantly reduce the harmonic content around the switching frequency of 2700 Hz. This is due to fact that inverter 1 carrier phase is set to +90, so switching harmonics are then partially cancelled. Okay, these are analysis of PCC voltage. Okay, these are the reference we referred in this example for modeling and analysis of inverter-based microgrid with Droop Control Technique. Let us see the example. These are a Simulink model of this microgrid islanded operation of inverter-based microgrid with Droop Control Technique. These are subsystem. This is a control subsystem. Here these were Microgrid Supervisory Control. As we discussed, you double click on Microgrid Supervisory Control. You need to set the frequency and line voltage, and also frequency regulator part and voltage regulator part. This is a 0.03 and integral gain is 2. Similarly for 0.1 and 7. Here measurement in terms of 10 and sample time is TS value. Here these are inverter. First is inverter subsystem and the 300 kilowatt subsystem, second one, and final one is a 200 kilowatt subsystem. Similarly, you need to set the values. The inverter 1, that is a 500 kilowatts inverter. So parameter, set the parameter value, power 500 and frequency 60, and primary line voltage is 600 and secondary line voltage is 480, and you set the frequency and voltage droop 1% for frequency and 4% for voltage. Similarly, you set the voltage regulator as you discussed in the time of presentation. Just you can see the block parameters of the 3 inverter blocks. Okay, here what is the PCC workspace? In this workspace block, what is the variable name for measurements? This 2 workspace block is used to specify time series array or structure in a workspace. For menu based simulation, data is written in the Matlab based workspace. What is a workspace means? Here after simulation we are getting the values in the form of table. Okay, now let us see that the time of simulation we can see. Here you set this structure with time format. Okay, or you need structure format, or you need array format, or you need time series format. In this example we set this saved format is structure with time. Just you can set this one, and the next one is a load. Different types of loads, 3 different loads. So let's load 1, load 2, load 3. Here y grounded and active power you set is 400. Similarly for load 2, Here 50 active power, Y grounded, and frequency and line voltage are same. It's a three-phase voltage, that is a three-phase dynamic load. We are there is a variable load. It implements the three-phase, three-wire dynamic loads. Here active and reactive power absorbed by the load vary as a function of positive sequence voltage. So that we need to give the initial positive sequence voltage and active and reactive power at the initial voltage also you need to mention. Okay, at the time of simulation, we are getting this PCC measurements, PCC frequency in terms of hertz, and power at PCC bus, reactive power and active power, and also you need to set the PCC VAB voltage. Okay, here FFT Analyzer app to compute the fast Fourier transform analysis of the simulated data. What are the data are there? You can see here. Now after this one, we are getting the values in the workspace. Similarly, at the time of simulation, you can see the plot. There is a first plot is inverter scope plot, and the second plot is PCC scope. It shows the reactive and active power, frequency, and also this one. Okay, now we can see the first is see the inverter scope. Okay, it normally it starts with this 0.1 second. Okay, it shows the legend values. Also, by using this measurement block, you can see the trace. In this trace selection, you can see the measurements of three different inverters. First one is 500 kilowatts inverter, and 300 kilowatts inverter, and 200 kilowatts inverter. Where we measured the power, measured power. It's active power and reactive power. The skew values it shows. Then after one, the same thing, the signal statistics. And signal statistics, you can see the bi-level measurement. Also you can get this peak finder value. Peak finder values also you can see. Similarly, this graph shows these legend values. That is where measurement, cursor measurement, and view the legends. View the legend values also you can see. There is a power at PCC, active power and reactive power. You can see this one, frequency, all the measurements, all the signals, frequency, and active power and reactive power at PCC bus. This scope shows the common point of common coupling bus measurements. It shows. The next one, the parallelly you can see the power FFT. Just you can type this one, you will get this Matlab interactive power FFT Analyzer app. Okay, now you can see these values. You can set these values like this. Okay, here the dimension parameter is set to 1. Okay, now normally the empty list is shown. After simulation, you will get this VPCC, and this zoom on FFT window will enable. Okay, now simulation is still going on. Okay, in the parallel you can see the maximum peak finder and all peak finder values. Okay, see, you can see these values. Also you can generate or print the figure. There are access scaling options and measurements options also available. Here you can change the layouts, you can change the configuration parameters, and Simulink snapshot also possible by using this one. Similarly for this PCC scope measurement, here itself you can see the peak finder. Peak finder values also you can see. This shows the empty list a structure with the time variables that exist in the Matlab workspace. Now you can see. Now we set the stop time is 8. almost 90% over. Now let us see the graph. Now it is finished. It's a PCC scope, and next one is the inverters scopes showing the measured reactive and active power. Now it is completed. After simulation over, the signal log will be available. So now you can see the FFT Analyzer app. This is a empty list structure with time. Click to update here. Okay, here if you click update, what are the PCC common point block to workspace block? Can you set the VPCC voltage and zoom into this? It shows the selected signal with FFT window. Okay, you set this FFT window, you will get this type of FFT, and what is the starting time and number of cycles and fundamental frequency and maximum frequency. You set these values as per values. That is our PCC voltage. Dimension parameter is 1, and set the zoom parameters FFT. The start time parameters to 7.9. Similarly, you give the 7.9 start time. You set this 7.9, and maximum frequency parameter is 700. Maximum frequency parameter is 7000. And now we click this. You need maximum frequency for total harmonic distortion computation is Nyquist frequency as same as frequency you can set. Display style bar chart or and the list are relative to DC component or relative to specified base or relative to DC component. You can select as your wish. This is a frequency in terms of hertz. Now we click on compute FFT. What will happen? It shows the graph between magnitude versus your frequency. That is a total DHT value is 2.85. The fundamental 68 frequency is for 489.8. Okay, similarly you can see double click on inverter 2 subsystem and change the carrier initial space. Now carrier initial space value, this one, this carrier initial phase value 90 degree, initial minus 90 degree. Set the change the minus 90 degree values and rerun the simulation again, and see the FFT analysis on PCC phase A voltage. Here you need to set the values at minus 90 degree phase. Okay, similarly you can apply and rerun again. You will get this THT analysis window by using this interactive FFT analyzer, power FFT analyzer app. Okay, in this example it shows the 28 and 29% are there. Based on this, according to your inverter scope and this VCC scope, clearly you can understand. In the example illustrates the islanded operations of parallel connected inverters with Droop Control Technique. I hope you enjoy this video. If you are new viewer of my channel, means kindly subscribe and like and put worthy comments on my YouTube channel. Thanks for watching. Thank you.